Those who follow my channel know that I have energy that I use. This is a power station that was once used in one of my projects. I decided to redesign it in a new case to make it look neater and more stylish. I have already created several different power stations. I have a battery box stored in the garage. It's a self-heating renewable battery. A very cool box. I put a lot of effort into it. I installed an inverter, fans, and other components. I also have a power outage kit that includes a small 20 amp-hour battery. A few years ago, I built a power station based on a lead-acid battery with a solar panel, but now I no longer use it. It has become outdated. Today, I want to show what I have done with this station. I have several videos where I explain how I built previous models, but today I want to focus on what to consider when creating a power station, such as components, wire sizes, crimping, and more, so you can understand which direction to take. When it comes to the advantages and disadvantages of a homemade power station versus a ready-made model like AFRE, I have several reasons why I prefer homemade. Both models have their advantages, and I like having both. The ready-made station is very convenient, but my homemade one has its benefits. Firstly, I have a refrigerator connected to a constant current, and it consumes about 40 to 50 watt-hours. During the day or night, he takes about 350 watt-hours from a system like this at 12 volts. For the finished AFRE model, this is about 30% of its battery capacity of 2,400 watt-hours, which means around 700 to 800 watt-hours just for the refrigerator. Meanwhile, my homemade station consumes half as much. The reason is that it is a 12-volt system, while the internal battery has a voltage of about 40 to 50 volts. This means an inverter must be used to convert the battery voltage to 12 or 24 volts, suitable for my refrigerator. There are losses in the process. The same applies to alternating current. My station has a 1,000-watt inverter, while the finished model has more than 2,000 watts. Regardless of whether you connect a device of 50, 100, or 1,000 watts, the inverter will be the same. I have several different inverters, one for 1,000 watts, another for 1,500 watts, and a small one for 300 watts that connects to the cigarette lighter. So, depending on what I use, choosing the smallest available size will minimize losses. When it comes to your home, it's not that critical. However, if you are assembling or using such a system, every watt matters, and you want to use as little energy as possible, especially in emergencies or while traveling. First of all, this can be done with a box that I assembled here. I will show you how I did it. You can also choose a box like the one I have in my garage, but such a box can be quite expensive. The particle board I used cost me about $60, so the choice is up to you. It may be difficult to find a box of that size, but I'm sure it's possible. Now, as for this box, I just sat down and began to ponder what exactly I want, what size I need the box to be, where to place the components, and so on. I wrote down all my ideas. I have a tablet on which I take notes and draw diagrams. Probably, I am the only one who can decipher my notes, but it helped me get a clear idea. After that, I started collecting a box. In the end, this box is 29 inches tall, about 2.5 feet, and 1 foot wide. This size turned out to be successful because I needed space for the fuse block and the inverter below, as well as a cutout for the battery located in the center. A height of 29 inches was optimal for placing everything needed, and a width of 1 foot fit perfectly, as the battery I have is 7 inches wide, leaving me 5 inches for maneuvering. I placed the battery 2 inches from the back wall and 3 inches from the front, as I needed only 2 inches of free space on one side for these tires. I don't plan to move these tires much. On the other side, I left 3 inches so the wires wouldn't be cramped and wouldn't interfere. Thus, the battery is located in the center. The top and sides are well aligned, but the front and back walls are slightly off by 1 inch. This is not critical for ease of transportation. In addition, I wanted to ensure that the box could hold 100 pounds so I could lift it without the bottom collapsing. For this, I used 3/4-inch plywood. OSB can be used, but it is not as strong, though it will also work. The battery weighs only 61 pounds, and the components inside, I think, add about 7 to 15 pounds more. So 100 pounds is a bit of a buffer, but if I add something later, it won't be a problem. I used 3mm plywood and first cut out the bottom. Then he attached the sidewalls to the bottom. I didn't fasten them from the top because it gives the structure more stability and strength when the screws are driven in this way rather than vertically. I installed 5 screws on the sides and 3 on the top and bottom, making the structure quite sturdy. I also added 3 screws on top. This will provide reliable support, and the battery will hold without problems. Later, I will install the cover and talk about it a little later. Then I decided where all the components would be located. This brought me back to the blueprints, where I sat and carefully thought about where everything would fit. I made sure there was at least 1 foot from the bottom to the top for the inverter to fit freely under the lid. I planned how it would be arranged and secured it with a strap to prevent it from shifting. Before installation, I cut holes for the front components, painted the box, and made sure everything was in place and the wires were tidy. I installed the tires and battery monitor on the back side. I drew on the front of the box where all the elements would be placed and at what level, as I wanted to leave a few inches at the top for a possible shelf or something similar. At the moment, I have a small accessory box, and I wanted everything to be positioned below the battery itself, except for this switch. After I drew everything, I started drilling holes and cut out handles. I smoothed all the edges and then painted the structure. I used spray paint, but perhaps it would have been better to use latex paint. First apply a primer, and then 1 or 2 layers of the chosen color. I chose gray because I like the contrast between black and gray, similar to the style of my Avery. But you can use any color you like. After I finished painting, it was time to put everything together. First, I cut the bottom so the battery would have its place and not move, as I didn't want wires dangling, and the battery needed to stay in place. I also made a cut for the inverter so that it fits securely with the strap. Then it simply fits into the bottom part of the structure. It is cut exactly to the size of the inside of this box. It works quite well. As for the lid, everything is pretty obvious here. You just need to cut it to the size of the box from the outside. The outside dimensions are 30 inches by 12 inches or 30 inches by 1/4 inch by 13.5 inches. The lid must be exactly the same size. I found these interesting hinges on the site that provide a smooth closing. This is convenient as the lid does not slam shut. It also holds the lid open in the upright position, so I don't have to worry about it leaning against the wall or something like that. It is positioned at a 45-degree angle, and when you close it, it closes smoothly. I will leave links to many things I used in this video in the description below, but these are different types of hinges, bar hinges, as well as regular hinges if you want. Then I started adding all the different components. Before we get to what I did with them, I want to quickly mention safety measures, because it's very important when assembling your own battery box. Fuses, fires, and wires. This is really important, especially with power supplies already prepared. In this case, everything is done at the factory, and you don't have to worry about it. When you assemble something yourself, that's when safety questions arise, because you don't want to cause a fire. The main danger is not in the battery itself. Life P4 batteries are really good because they have a battery management system. They are much better and safer than regular lithium-ion or lead-acid batteries thanks to this system. The danger lies in the components around the battery and the wiring, as well as how well they are crimped and whether the wire sizes are appropriate. Therefore, it is very important to ensure that everything is done correctly, because when it comes to 100 amps, you don't want the wires to overheat and suddenly cause a fire in the box and then on the wall. Make sure you think about this and that everything is properly secured. I have a 100 amp fuse that goes straight to the battery terminal. This battery is 200 amps, which means I can draw 200 amps from it if I want. But I don't want it to be that way. My wiring is rated for a maximum of 100 amps, and that's already at the limit. So I installed a fuse to make sure I couldn't exceed 100 amps. You want everything to be fused in the distribution panel. Don't forget to fuse everything you can. The inverter is not fused because I have a fuse on the battery right by the positive cable. So, it's not necessary, but I have a few extra fuses. I could install them when I connect this device. And a little later, I will show exactly how I connect it. But if I ever disconnect this and reconnect it, I can set a fuse if I want. Amperes are an important aspect when choosing wires. It is the amperes that create heat in the wires. An amp is the current that flows to and from the battery. Therefore, it is important to understand that the wires must withstand the required number of amps. I have a table that I use constantly, indicating which wires are suitable. For example, wires of 10, 4, and 6 to 8 gauges. They go to the fuse box, which is located here. I will probably upgrade this to 6-gauge wires, as it specifies how many amps can pass through them. This needs to be considered when connecting everything to the battery. I have the biggest cables since everything comes from the battery. These connectors at the front use wires of 10, 8, and 12 gauges. They don't carry many amps, so they don't need to be too thick. For instance, the battery monitor I have here connects directly from the battery to the fuse and distribution bus, requiring thicker wires, so make sure to use appropriately sized wires for each purpose. And if you are planning an upgrade in the future, make sure it is done in advance. Instead of using 4-gauge wire, You can use 3 or 2 gauge wire, especially if you are going to connect an inverter with a power of up to 2000 watts or something similar. You may need really large wires. It's important to pay attention to this. Wires, fuses, and safety are key points, while power stations like this one already have everything necessary. Let's talk about the components I installed here. Let's start with the battery. Imagine it as the branches of a tree. You have a battery that is the trunk of the tree, and these bus bars are the first 2 branches. Consider them as extensions of the battery terminals. You should not connect 4 or 5 different components to one battery terminal. These buses allow for load distribution. This switch, for example, goes from the battery to the switch and then to the positive distribution bus. Here, I have a battery monitor that shows the condition of the battery. It's a very good Victron monitor. It connects from the battery to the distribution bus. So, this essentially becomes a new terminal connection for the battery, positive and negative. Here, I connected the inverter terminal using a wire with a cross-section of 4 square millimeters. It comes out at the top where the Anderson SB125 connector is installed, allowing me to connect the inverter with this cable. I can link it to the inverter and connect it to the battery bank. Then I can mount the inverter on the lid of this box and use it that way. I didn't want to put it inside the box and leave it connected all the time, as I use it quite rarely, perhaps only once or twice, and only for demonstration in a video, so there's no point in keeping it inside a box where it can overheat. The same goes for the charging controller, represented here by the OptiSolax controller. This is where the solar panels connect. He connects using the same Anderson connector, but SB50. The connection goes to the charging controller, which is a compact S1 model from OptiSolax. A very convenient option. It heats up a bit, but not to a critical temperature. I wanted him to be outside so that the temperature inside the box wouldn't rise. The solar panels connect through MC4 connectors and this small collector. Inside, the wires can be seen entering and rising to the bus. Thus, the charge controller and solar panels are connected to the bus and power the batteries through these buses. I also have the next set of branches on the bus. This is a fuse block for smaller components. If we imagine these buses as the first branches, then from them extend further branches connected to this fuse block. The fuses connect to the buses and go to the components located at the front. Here I have the opportunity to recharge using an AC charger. It's only 10 amps and I use it rarely, but if the weather is cloudy for several days and I've used a lot of amp hours from the battery, I can use this 10 amp charger to slowly restore the charge. I also have an XT90 connector for my direct current refrigerator. I modified the refrigerator cable by replacing the connector with an XT90, as it is more reliable than cigarette connectors that can sometimes slip out. I also need this connector for the inverter. I can connect my small 300-watt inverter here, although this outlet is rated for only 200 watts maximum, so I don't want to exceed that limit. There is also a power button here. I have several different ports, including USB-C and USB. It is very convenient if you need to charge mobile phones, tablets, computers, and other devices. I can also use them to transfer energy to other batteries. All these ports are connected to a small fuse block, which, in turn, is connected to the buses. These tires are powered by a battery. You could say they resemble tree branches that all lead to the root, to the battery. In general, that's all I have. I have a battery monitor, ports in the front, and I can add anything in the future. For example, if I need an Anderson port or something similar, I can install it. However, if I decide to upgrade my equipment and install a 200-watt inverter, I will have to replace all the wiring here. This may be impractical, so if you want something like this, it might be worth thinking about it in advance and using thicker wires. 2 large wires won't be a problem, but 2 small ones could cause a fire. I also have a cart on which everything stands to make the system portable. One person can lift it, but it is a bit wide and heavy, so it's easier to do it together. The cart allows me to move the setup without having to lift it constantly, which is convenient for the whole family, not just for me. I don't plan to use this inverter often, as I don't need it regularly. Primarily, it will be used to connect my IceCo refrigerator, which operates around the clock and is constantly plugged into this unit. Also, if I need to charge any power stations or small electronic devices like tablets and phones, I can connect them to the ports. It won't be used very much, but it will be on every day. In case of an emergency or if I take it with me on a hike, I can connect the inverter and get alternating current for any needs. Overall, it turned out pretty great, and I really like it. At the moment, my favorite is the battery pack for the garage with a capacity of 100 amp hours, which is assembled very well and is compact. But I like this option much more than the large cart I had before. The cart was good because it clearly showed how everything was connected. If you are going to assemble something like this, it might be worth watching a video about it to see how everything should be organized, rather than just thrown together in one place. I really like how it looks. The house became much tidier and cleaner than if a large cart were here. I can use different components at my discretion. I can connect a solar panel here. I can connect a solar panel to these batteries. If I want, I can connect an inverter. This device has many different applications. It will consume less energy than one of those power plants. Although those power plants are much more convenient, this solution has its advantages. Also, if any part here breaks down, say the inverter stops working, or the bus fails, or one of the wires comes loose, the entire block will become unusable. Most people won't be able to replace such parts. Here, it's enough to simply take out the battery or switch this switch, disconnect the battery, then replace any of the necessary components. After that, you put the battery back, turn it on, and it's all ready. You simply lift the lid and everything works, unlike taking apart one of those setups. If I haven't answered your questions, or if you have others, feel free to leave them in the comments below. If you plan to assemble a similar unit, let me know. Or if you already have something similar, for example, you used a toolbox, tell us what you did. That's all for today. As I said, if you have questions, write in the comments. Take care and prepare. Good luck to everyone. See you.